So I was, we were part of the ASCII's Flash Center at Chicago, got to use some cool machines, did, super, bread and butter HPC things, Fortran, MPI, Octree, grudgingly started using OpenMP when I came out. And so, after doing a postdoc, I ended up joining an HPC center after the postdoc and started working with various scientists doing very different things in very different fields. And so I entered the field during what has to be the most exciting period in scientific computing probably ever, right? There had been, at the start of my career, was sort of the tail end of 20 years of stability. Big computing was a bunch of x86, some MPI over some sort of fabric. No one outside of academia was doing a ton of numeric computing, at least in the open literature. And there was a pretty stable set of problems. And so suddenly I found myself in a very different environment. And it's fantastic. New communities make things interesting. There was the internet scale, companies bringing in huge amounts of data, doing really interesting image processing or machine learning, using some familiar and some unfamiliar methods. The genomics community came in, and they all started building their own frameworks. New hardware makes things exciting. The large number of cores per socket, and the FPGAs coming up, non-volatile memory, and the raising bar for computational science made things interesting. So in my own field, sort of at the start when I was learning, fairly simple problems were cutting edge. Gravity-only problems, watching a bunch of non-interacting but gravitating particles fall in and form a galaxy. That was cutting edge in the 80s. And then the 90s, add some fluid dynamics on top of that so that the fluid would splash together when the collapse happened and the stars would ignite. And then, doing this on a cosmological scale, thousands and tens of thousands, hundreds of thousands of galaxies. And now adding radiation transport, so these first ignited stars push away some of the fluid, protecting their turf, feeding back on the hydrodynamics. So, things were just super, super exciting. So in 2013, I started becoming more and more interested in genomics. The huge computational needs, very interesting, deep algorithmic challenges. And so, HPC to the rescue, right? I will teach these people how it's done. So in 2014, I moved to the Ontario Institute for Cancer Research. Jared Simpson was kind enough to take me under his wing. He was he started his career as a video game programmer, so he was welcoming to people outside of biology. And Jared, amongst other things, other credits, wrote one of the first open source sort of human scale de novo genome assemblers. So taking the next generation sequencing reads and actually being able to tackle fairly sizable genomes like the humans, actually assemble it, and it was MPI based. So this seems natural enough. Well, Abyss 2.0 just came out with a new non-MPI mode, and that's going to be the default now. And there's no interest in future MPI algorithmic development. In the meantime, one of the de facto standards for genome analysis, the Genome Analysis Toolkit, just came out. And it supports cluster computing finally, but using Apache Spark. And I should note that Abyss 2.0 isn't even doing that. It's just using ginormous shared memory machines. So that's sort of my checkered past, the idea that I'm interested in a lot of different scientific fields. And so this is my view, trying to go through and look through the evolving landscape of computational frameworks, programming languages for dealing with big computing for scientific problems. Look at some of the problems. A tour of some of the programming models that our team has tried to use. And from that vantage point, after finishing that tour, take a look at where CHIUW fits in all this from our point of view, and what nearby territories in the landscape are fertile. My perspective is based on the problems I've worked on. That's the case for us all, but it's useful to spell these out, I think. These are the problems I have in mind when I'm walking through these technology, this landscape, and either walking towards or away from the technology. So I started, like I said, with very traditional fluid flow stuff, high-speed reactive fluid flows, reactive, either fixed grid, structured or unstructured, or sort of block-structured adaptive. So you have a mesh full of blocks that themselves contain cells, and if you need resolution, more resolution there, you refine the block, adding more blocks. So, that was in my grad school, which was some years ago. So now I'm working with genomics data. So very different problems. So you take a bit of person, rip out the DNA, chop that into tiny, tiny fragments, feed those into a next generation sequencer, and out comes 10 million, 100 million little reads. And now we have to stitch these together into the genome. And assembly isn't actually a task that you necessarily need to do all the time, but it's a pretty good model for the sorts of things you need to do with reads data to extract information. So you have these small little fragments of DNA. You're looking for overlaps between them and building a graph out of all those possible overlaps. And then at the end, you walk through this graph, traversing, looking for the maximal unambiguous sequences that you can extract from this, and those are your contigs. Now you're just about done with your assembly problem. But there's simpler analysis you can do too. That's also sort of revolves around these substrings. Even just breaking the reads into substrings and counting them, counting how many AAGs there are. That would be longer than 3, but counting these k-mers is interesting. It can give you a fingerprint of what's in the DNA in the cell. So, for instance, you can do things like take some bacteria from a sick person, do this sort of just quick k-mer counting, which is very, very fast, but requires you to be able to count substrings, which is very, very fast, and then look to see if that spectrum, that distribution of counts you get, is consistent with, the sort of thing you'd expect if the bacteria were, some known pathogen. So this can really matter because if you take some virus or some bacteria to a path lab, it will take 2-3 days to develop a culture, and then the pathologist will look at that and say, oh yeah, that's clearly the Nova Scotian death flu. You don't put that. Whereas this is something that can in principle be done fairly quickly. The other sort of problems I'm interested in is just sort of bog standard but big biostatistical analyses. And so this is closest to my day job now, where we have hospitals or health centers across Canada. But in Canada, healthcare is exclusively the domain of the provinces, each with their own different rules about sharing data. So the idea is to be able to feed queries to a distributed network of private data stores, get partial results, and somehow amalgamate that into some final answer for a researcher, so that Canadian researchers can make use of the entire country's health data, even though they don't necessarily have access to it. Obviously, that's more easily done for some sorts of problems than others, but there's a lot of problems that can be done. But even just more mundane biostatistic samples. So say RNA-seq. Our cells all have the same DNA almost exactly, but our skin cells are very different from our blood cells, very different from our brain cells. And that's largely because some of the amount of DNA so the DNA is all the same, but it's configured slightly differently or marked slightly differently in the cells as they evolve and grow. So different regions of DNA will be hidden or marked, don't read me. And as the cellular processes read off DNA and translate it to RNA, so the amount of different genes that are expressed will be very different cell to cell. And that's not just true of different tissue types, it's true of disease. Some process will be going rampant in some cell, and so the DNA, the RNA expression data will be very different in that. So imagine RNA sequence expression data, you get 100 million fragments of this little sequence. It's imperfect, very imperfectly sampled in some cell. These are then computationally matched up to which gene transcript they correspond to, and you count them, and you find out if that, the gene, some particular gene is transcribed differently between a healthy cell and a sick cell. Now do that for multiple tissue types, then do that for a large population, and then start integrating other data, correlating that data with phenotypic data, what symptoms the patients have, or what DNA variants they have, or just clinical data, demographic stuff. So, bog standard, but can get quite big statistical analyses. So these are the problems that sort of are nagging at the back of my mind when I take a look at the evolving lay of the land. And this is sort of a view into Jonathan Dursi's view of the world, how the computational landscape, scientific computing landscape evolved over the years. So I was safely ensconced over in Physical-landia there, doing MPI, OpenMP-ish stuff. There were colleagues doing desktop sort of analysis or simulation with Python or data. There were rumors told across campus and past the Badlands of people in the social sciences doing statistical analyses with SPSS or Stata or a new hotness called R. Well off in the distance, there was a land of SQL that some people were doing. It seemed suspicious. We didn't go near it. But apparently there was communication up and down this river between this SQL people and the statistical people. And there was occasional ferry service between the MATLAB folk and the SPSS folk, but that was about it. And we all had our little territories, and we were pretty happy with that. And then they came. So like 2006, 2007, finally computing was everywhere, data was coming in everywhere. It started with the internet scale folks who were the first sort of businesses who had tons of data they wanted to analyze, but soon others followed. And then of course the genomics folks who were just sort of in the right place at the right time, coming off the success of the Human Genome Project in 2003. And then next generation sequencing, high throughput sequencing was starting, where they could get suddenly hundreds of millions of reads for $50,000, then $20,000, then $10,000. So they brought all this new infrastructure and all this new need for data along with them. And so my view of the world, which is a little distorted, sort of looks like this now. So the big data, the people who had lots of data, they found some willing collaborators in the data handling communities on both sides of the Badlands. The statistics people doing things like R, they were really into this. This was great. They really came of age. R could not have been becoming popular at a better time. It's just amazing. The Python, especially the data analysis side, they just went nuts on this newly fertile territory. Just adding project after project after project. The genomics people set up camp, sort of found their little niche. So it's a very different world. Us simulation people have always been, which made up most of traditional HPC, have always treated this stuff deeply skeptically. Some of this is not invented here. Some of this is just different confused by different languages. The needs seem very different terminology. It didn't help that the initial tools were clearly not going to be helpful for simulation folks, right? So Hadoop MapReduce, it was all out-of-core stuff, and this calculations were doing very simple. So some combination of different terminology and initial, just first reactions to things. There's still some skepticism here, but my argument is that this is all a continuum now, that these things aren't that different. They might have been more different before, but as simulations are getting more complex and dynamic, and as big data problems are getting more mathematically sophisticated, they're sort of lurching towards each other in fits and starts. So for instance, almost any sort of numeric computation requires linear algebra. That's sort of literally a law of mathematics. You're not going to get very far without linear algebra. The only real difference in big data sort of problems is that the linear algebra is always sparse, which isn't that different really, but the sparsity patterns are even more extreme, which mean they need slightly more sophisticated methods, or make do with less sophisticated methods for dealing with the weird sparsity pattern. But as simulations get more and more complex, the sparsity patterns start getting weirder and more adaptive too. It's exactly the same thing with the graphs that the big data people are dealing with. It doesn't look so much like a traditional unstructured mesh anymore because of a power law distribution and the number of edges a vertex has. For some reason, in Twitter, fellow Canadian Justin Bieber has significantly more followers than I do, even though I think I offer very cogent insights on matters of the day. But still, it's the same thing. As these simulation stuff, as the networks people want to analyze get more complicated, they start looking more and more like this too, and they're decomposed in largely, not always, the same way. And these sorts of computations that are done, map not that crazily onto unstructured mesh computations. In fact, in some ways, the unstructured mesh computations are easier because once you get all the data from neighboring vertices onto yours, you actually have more computing to do on them. It's more numerically intense. Whereas the sort of things you do on network graphs are very, very simple computations. You're doing sums or means or something. So that the big data graphs are typically more latency sensitive than ours. So in some ways they're harder. So these problems aren't all that different. At least they won't be. So this is why I sort of wandered afield and was looking at big data technologies, and that's where my sort of MPI post, which was not supposed to become as popular as it did, or popular is maybe a funny word, well read as it was expressing. So let's start taking a look at things that I or my team have been looking at for different problems. So R is an obvious one. R is something that we're looking obviously for more of the biostatistics type problems. Who here is not familiar with R?
Depends on the definition of things.
Well, people know what R is, right? Okay. I will say it's huge in biostatistics. There's this sort of different package store bioconductor. It's just huge. R's popularity was not a given. Even getting as far as it did up to 2002 was not a given. There were many very established incumbent packages out there. And the danger is always that you publish something with a new open source statistical package instead of something that's well established in the community. And the worry is the referees say, yeah, run it again with this thing I actually know something about. And the thing is, this fear can be stifling even if it's not actually real, right? You can hinder adoption, especially in academia, just by you being worried that other people are worried about a package. But eventually, it was free, easily extensible, high quality. It took ages to catch on, but it did. So This is what data scientists use in the course of their day, and R is on top and just smokes everything else. So my first lesson to take from this is that incumbents can be used. This is the number of academic papers, again, a little bit more conservative, published with using different statistics packages. And here we see the rise and fall of some of the incumbents. SPSS on top here, and R gathering steam. This is a bit of an old font. But the second lesson is growth is slow until it isn't. And of course, finally, I think, and this has already come up, that a big reason for deciding to use R is that the packages are available. These high-quality user-contributed packages to solve particular problems for them, and then other people adopt this idea that the user's contributions can be as important as the implementers. Now I want to talk a little bit about R and parallelism. So the fundamental data structure of R is the data frame. Think an SQL table or spreadsheet or something. It's a list of typed columns, 1D array of record. It's not rocket science. And of course, it's the sort of thing you can easily distribute over multiple machines, right? You just vertically partition it. So you might hope that there would be a vibrant parallel R ecosystem. We've got this data structure which is very clearly decomposed. They have ways of users to contribute packages. So it should be great for parallelism. And sure enough, if you look at CRAN, the package place, there's a task view for high-performance computing and parallel computing. There's a lot of things there. So it's great for parallel computing. The problem is all of those packages aren't actually, they're not necessarily a sign of a healthy ecosystem. They can represent the output of a wheel re-implementation factory. R has several high-quality, now some of them are in core, parallel tools. But they don't work together, and they implement a few primitives and nothing on top of it. There are some very good parallel packages for some specific tasks that have been built by people with an enormous effort, way on the other side here. But in between, there's this chasm of despair. If you want to program something, if you want to do some parallel analysis in R, and someone already hasn't built a tool for you, and your parallelism isn't nearly trivially expressed, you're just out of luck. You have to buckle down and spend a year and a half writing your own thing. And so far, none of the, there's no carrot library that other people can use that can help get you over this chasm. You're either on one side or you aren't. And this is a problem. Scientists don't want to write parallel code that will enable an entire community. They just want to publish their papers. So decompositions of data frames, it's a trivial thing, but there needs to be composable parallel tools, which R doesn't have. So Spark's a little different. People's familiarity with Spark? Who here's used Spark? Like fired up a PySpark job? Not much. Okay, so a couple people. So Spark beat out Hadoop MapReduce because it was so much faster. Hadoop MapReduce went through disk every iteration. Read the whole data set off disk, spat it back onto disk. And this is one of the reasons the simulation people were deeply skeptical. So Spark is built around these resilient distributed data sets and tables of rows. They're immutable, restricted to certain transformations. And so being in memory was a huge performance win. Huge performance win over MapReduce. So it just completely ate MapReduce's lunch. So performance is crucial to a point. In 2002, this is logistic regression up there. Either of these benchmarks would have been completely blown out of the water by MPI, even done fairly crudely. or any of a number of HPC frameworks. There was no multi-core in either of these things. Using generic sockets for communications, there's no GPU support. They're all JVM based, so there's garbage collection, jitter, and pauses. This would have, you could blow this away with MPI. But people weren't going to write MPI. The amount of development time, the lack of fault tolerance, no integration into the ecosystem means that MPI isn't even in the running here. The relevant comparison isn't MPI. So things just have to be fast enough. And so I heard this morning talk that, so Chapel's performance has been coming leaps and bounds. And I still hear comparisons from a number of places that, yeah, but it's there's some case where it's only 60% as fast as MPI or something. Yeah, well, it's even slower if you compare it to, custom-made ASICs into a special cluster just for that problem, right? But that doesn't matter because people aren't going to do that. There are people who will sit down and write MPI, but the competition isn't necessarily people porting code over from MPI. The competition is with people who are either not going to write a program or will write something small in Python and do it on a few nodes. So, Project Tungsten in 2015 was an extensive rewriting of Spark for performance. Got rid of JVM. They handle their memory themselves with something that looks like Fortran 77 workspace arrays. Nothing is truly new. Vastly improved cache performance and whatever. So, and they built in GPU support 2016. So there's always going to be pending performance improvements. They're important, but they're not showstoppers. The sort of other lesson here is that big data frameworks are importing HPC lessons faster than it's going the other way. And I'll just say this one more thing about Spark. These transformations that are built in, things like map, filter, reduce, join, group by, stuff like that, with RDD plus those are enough to start building databases, key value databases. They're enough to build data frames on, sort of R-like data frames. They're enough to build a graph library on, a very capable now graph library, GraphX. So sort of and if you have a perverse sense of what's fun to do, you can actually use the Spark GraphX library to write little unstructured mesh codes like 2D ejection. So this is sort of the flip side of R. The right abstractions, the decomposition with enough of these primitive reactive operations and ones that are well thought out enough can be enough to build an ecosystem. So there's been relatively little uptake in the sciences on Spark of sort of individual scientists. And it seems weird, let's say in genomics, this graph library seems like it'd be very natural to do genomics graph things in. The large statistical analyses seem very nice. GATK is using Spark, but that's a bit of a special case. GATK is more research infrastructure. It's something it's like a centrifuge or something. It's something you take the data into. Eventually, it's a product that spits out the variance or whatever, and that's the start of the research project. But actual scientists in their doing research time are not using Spark. My claim is that this is because of a scaled down problem. Spark is an incredibly heavyweight system. You have to have this entire Spark cluster running. The runtime is incredibly heavyweight. And this is an awkward fit for scientists, how they actually work. They noodle around on their laptop for a while. They write a method. They try it on small data, make sure they understand it, and then they scale up. And Spark is really just not good at that. Spark is great if you already have some ginormous, data warehouse or data lake or, I don't know, data swamp, whatever. And you have production tools that people are using it on. But that's just not how science works. If we already had all the data and all the infrastructure to do it, that wouldn't be science anymore. So scale down is really important. So that's where tools like Dask come in. Dask is a parallel Python package. It's very easy. It scales down very easily, and it's getting adoption because of libraries. So you build, a bit like Spark, you build explicitly a task graph. Then it goes off to a scheduler and optimizer, which discards unnecessary tasks. Memory use is kept low. Intermediate results are relentlessly pruned. If a task dies, it's restarted by the scheduler, so there's a crude sort of fault tolerance. And it has support for distributed arrays. And one of the nice things is it has support for out-of-core computations on distributed arrays. So this makes scaling down even more interesting. You're not going to run out of memory on a problem, even if you're trying now a big data set on your desktop. It'll just take a while because it's doing out-of-core stuff. So, this is becoming really interesting, not so much for the PDE stuff, although it's possible to do it there, but for the data analysis, biostatistics things, this is starting to be interesting. And it's not inconceivable that it could do something for graph problems on this too. There's tools like tensor overflow, or TensorFlow. TensorFlow? Familiarity? TensorFlow is cool. I don't want to spend much time on it though. It seems natural. It seems a natural fit. You're dealing with big multi-dimensional arrays. It has support for distributed computation. Again, you have data flow graphs which can then be optimized. And in a way, these are getting very close to traditional HPC problems, especially when you use TensorFlow for things like image processing or the like. The obligatory Mandelbrot set or a PDE example. So that the problem, there are things you can do with this. There's deep learning is typically done with some sort of time stepping or something like time stepping with updates of parameters. You can sort of wedge some kind of sort of, say, PDE type work into this. And great for very specific forms of data processing. But it's not, sadly, it's not going to be as helpful as I thought. Finally, Julia, which I wrote a little bit about last week. Julia is super cool in a few ways. Julia, it's a dynamic language, just-in-time compiled, multiple dispatch, rich types. So it gives you a scripting language type feel. And as Lisp-like comedic programming, code is data. And so these two combined mean that it's possible to write mini DSLs for particular problems, which perform really well but are really easy to use, really easy to express in problems. So this is super cool. And there's a full suite of parallel primitives. And this is what a Julia set looks like in Julia. So the single core performance is quite good, and Julia has been focused almost maniacally on single core performance. So yeah, I guess you'd expect it to be good, but still, for a JIT, that's pretty cool. But for these sorts of problems, NumPy and Numba also do really well. So I'm skeptical about how important being able to do trivial single core calculations really fast is. And this focus on single core has meant that even multi-threading is still experimental 5 years into the language. And I can't help but be a little skeptical of a numerical computing language that doesn't support threading. I mean, NumPy and Numba. Julia has a distributed array module that has huge overhead. There's only multiprocessing, of course, not multi-threading. And just starting up just with one distributed array, it takes hundreds of seconds to do anything non-trivial on. So this is where Chappell's hierarchical approach to parallelism really shines. So this is the tour, the long walk through the wilderness I went on. So where does this leave my curated set of benchmark problems? In some horrible parallel universe where there were no projects like Chapel, what would I be doing these problems in? So, for PDEs, the big data frameworks have, a big reliance on distributed execution graph optimizers, and that seems cool for highly dynamic simulation. But from where we are now, the big data frameworks are not going to save me from what the current state of the art is, which are really cool, enormous effort has gone into these sorts of libraries like Trillanos and Boxlib or whatever. But they're huge code bases, they're very hard to change, and it's very hard to even start with as a user. The idea of some grad student on their own just doing something in Trillanos or Boxlib, that's like an entire grad student career there. That just slows down progress. And they're all based on MPI, which I have opinions about. On genomics, the state of genomics really should make all of us in the parallel scientific computing field sort of hang our head. The large genomics today means buying a terabyte of RAM on a shared memory machine. We have failed, right? This represents failure. The good news is the bioinformatics community is doing lots of great algorithmic work on things like succinct data structures or streaming approximate algorithms to work around the fact that they have to fit in shared memory. But this is actually limiting the size of projects that are being tackled. There are individual projects like HIPMER, which is based, I guess, in C++, that does large-scale assembly. It apparently does it fairly well. But again, this is like one project on the other side of that chasm of despair, and it doesn't help anyone else cross that chasm. GraphX for Spark could actually be pretty useful, but it only becomes performant. It only overcomes its overhead on huge problems. And again, that's just not how scientists start working on things. Nobody starts work spending months or years developing a method and then tries it for the first time on 100 terabytes. They'd be mad to do that. The missing middle, going from the desktop and scaling up is where most of work is done. Most science is just done there. And it's important for adoption, too. Biostatistics is exactly the same thing. There's R on the desktop, which is awesome. Spark out really large scales, also awesome. And this can be useful, like big international genomics projects. They're just born knowing you're going to have to handle 4 bazillion, gazooba bytes of data, and they just build for that right at the beginning. But it's Death Valley in between. There's just nothing. So this is an example which just infuriates me. So I'm going to share it with you, lucky you. So the Broad Institute is using Spark. They're the ones who write GATK. So they're using Spark for this HAIL project, which is interactive data exploration, good stuff, of matrices of does person X have genomic variant Y sort of matrices. And it's not yes, no, it's a record that has probabilities and things like that. So you interactively query things that come down to reductions of sets of rows and sets of columns. These tables are maybe a billion elements in size, maybe a few billion. Right? This is not a hard problem. Right? This is not some sort of exascale co-design, right? But But what they end up using for this is Spark, even though it's enormous overkill. I guess you can say it's future-proof, but the fact that there's nothing else for doing that is sort of mind-boggling to me. And so this is where CHIUW comes in. So where do I, as an outsider, think CHIUW can or does in this landscape? So my opinion, as an outsider, after casting about for languages to do stuff in, is that CHIUW is important, CHIUW is mature, and CHIUW is just getting started. So if the scientific community is going to have some frameworks for solving scientific problems that are actually designed for our problems, it's going to come from a project like CHIUW. Using MPI as a framework just isn't sustainable as things get more complex, both on the software side and the hardware side. Big data frameworks don't have any incentive to support scale down. That's not what they're about. And they don't have any incentive to support tightly coupled computing. Again, that's just not what they're about. But scientists need both of these. And this is where a project like CHIUW comes in. And the thing about CHIUW is that the set of all things that are projects like CHIUW is CHIUW. There are other research projects in this area. And productive parallel performance computing languages for distributed memory for scientific computing. But they're research projects, and CHIUW, I think especially now, 114, 115 is a mature product, not a research project. It's crossing the barrier of fast enough. And when I wrote that, I worry that sounds disparaging now. Fast enough is high praise, right? Fast enough is a yes-no decision for a scientist. Is this fast enough? Like if this is 20% faster, I'll just harass my system until I get 20% per second. That's fine. Is this fast enough? And I think it's crossing the barrier for problems that map naturally to it, that it's fast enough. And that's the pieces to start expanding those problems. It has a very solid base. Right? It can scale down because it has native compilation and its runtime isn't some enormous Spark scale thing. It has good single core performance. It has strong distributed memory performance for rectangular, dense, or sparse arrays. It's an excellent set of parallel primitives and a small but well-chosen set of useful tools. So I claim, again as an outsider, that there's enough of a foundation to start building an ecosystem around. I claim that CHIUW is closer to Spark in that sense than R. But there's still a need to help users across their own sort of, not chasm of despair, but crevice of disappointment, discouragement. To make it so easy for a scientist to start using CHIUW for problems that it becomes too hard to resist. And the existing set of choices help with this. It helps because there's lots of excellent tools, and they're miserably difficult to use. And this is things that a growing user community can contribute. It does not necessarily all have to be on the developer's shoulders. So PETC is, I'm listing a set of ideas here that may or may not be practical or even good ideas. But again, from an outsider's point of view, PETC, anyone here use PETC? Okay. Well, on a scale of 1 to 10, how easy is PETC to get a grad student to start using?
Pain in the neck.
Yeah. So it's a widely used library for large space and sparse iterative software. And I promise you, right now, some grad student is sitting down, writing 500, 1,000 lines of code, which is going to populate a sparse matrix and do some linear solve. And they're going to write that up, and that's their code. That's the code they publish and do their research with. So it's very useful. It is the base of a lot of homemade scientific codes. It has an excellent and comprehensive library of solvers. And it's notoriously hard to get started with. It's hard for, I worked in the HPC center, it's hard to even install. A significant fraction of PETC functionality is tied up in large compressed the sparse row matrices of reasonable sparsity structure partitioned by rows, and vectors and solvers on top. What would a Chapel API to Petsy look like? What would a Chapel implementation of some cool Petsy solvers look like? How about scale path? It's not clear to me this is a good match, but what if it was? Graph and string problems in genomics is, it's a huge field, much, much larger than the field I come from, badly underserved. The competition is threaded or serial code on a single big memory machine. There's lots of very nice actual genomics code out there right now, which is done with Python dictionaries. And there's no equivalent of Numba or NumPy to help, to speed it up. So it's really just pure Python code. Is this something that's feasible to think about Chapel? Data science. This is again maybe one step less of a sure thing, but there's a real problem here that our parallel is kind of a mess, and Spark is kind of a huge thing to have to depend on. Python is making inroads. There are some pieces of a data science story here, but other things would need to be added. So this is where I think, as an outsider, things are. The beginning of a glorious age of expansion. Chapel has established a stronghold sort of on the edge of fairly hostile territory. But there are scientists in neighboring territories who need help, who need the sort of help Chapel can provide in almost any direction. So there are communities that would like productivity, performance, and desktop to cluster scalability. So I really think it is possible to start winning over user communities, and I would love to see it, because the scientific community needs stuff like this. And the other many options just aren't providing it. Anyway, so that's my view from here. Thanks very much.
Questions? Started saying the number of things that I agree with this presentation. It will be probably the same number as the number of slides you have. I mean, there's great things like scaling down, because if I can't experiment locally, I'm never going to invest in the large-scale runs. But I think there's one thing that I wanted to distinguish. As someone who was also in the Hitler team and also worked on graphs and genomics at the same time and matrices, once you either just want to experiment locally and Python is fine, okay? And then you now know that this is a core computation that you're going to be doing in data sets that keep coming every month, every week. And now at that moment, think of the assembly problem. It's the way you wrote this in Hitler. It took 2 years for 5 people, and it's huge. It's huge because the algorithms and the methods are huge, not just because of the communication thing. It's not the UPCs or APIs fault. So once I commit learning such a complicated code, nobody except the developers will be able to play with it anyway. So I'm happy to go to the most performant one. Now for the user, it's a very different story. I think what you want is a simple user that's going to call the assembler, that's going to call the variant caller, that's going to call whatever the thing. You want those guys to move to Chapel, but it doesn't matter if the inner core of that thing is written in Chapel or whatever the pain the programmer wanted to input on himself. That's what I was trying to say. I think once the code becomes over 3,000 lines, it doesn't matter how much pain you inflict. It's at that point, it's like enough to start and write a project proposal.
Sure. Yeah. So let me see if I can. Let me see if I can summarize. There's a difference between a code which is itself a research project and something that becomes productionized, which is now sort of a research tool. So this is sort of what I was thinking with GATK. Like GATK is not a research project anymore, right? It just becomes a thing and people run it, and absolutely, right, somebody's going to sit down and spend, real developer effort, and it's going to be a big thing. So I completely agree with that. There's the distinction between research projects and something that eventually becomes a product. So I completely agree. And there, because it's such a big deal, completely agree. You put in whatever effort you have to do. You use whatever tools are going to be the best. What concerns me is that the pipeline of research projects that can become products is being stifled, is being pinched off by the fact that you can only do tests on chromosome 21s for so long before you need, right? Before you need to be able to scale up and demonstrate that this thing actually works on whole human genomes, on sets of human genomes. And right there, I think there's this bottleneck, and I think it's completely artificial, and it's imposed by parallel computing community choices, not by biology choices. Does that sound fair?
No, this is so correct. I laughed because I actually didn't know this until a couple of weeks ago, that chromosome 1, 2, 3 is basic. For those who don't know, these are essentially sorted by size. So 21 is one of the smallest. And in fact, we're in this moment that I don't want to parallelize the code for distributed memory because I'm not sure if the idea is great, but the chromosome 14 is too big. Okay?
Right.
So 100% correct. Yeah.
So there needs to be something. And you're absolutely right. The final thing that becomes a product, exactly like you said, somebody's going to write a grant proposal for that. They're actually going to hire software engineers, and it's a different regime. So absolutely, and there you do what you need to do. It's that first stage that I'm really concerned.
Do you want to say a little bit about the need for interactivity?
I go back and forth on this. I think some of this comes down to the scientific workflow again. I think that noodling around on the laptop is really important. Half the time in scientific computing, the question we're asking is, will this even work? We survived for years doing the edit, compile, run cycle, but it does slow things down. I can't even tell you how often I have a Python window open, interpreter open, just to see if I've got the syntax of a line correct that I'm about to type into an editor, right? It matters. It does speed up it hugely speeds up the development cycle. I go back and forth on whether it's on Dursi's list of things that must happen for me to start adopting something. But I don't think there's any question, especially for the whole scientist noodling around on something, will this even work? Having interactive access to things matters. Both when you're developing a tool, but also for using a tool. Like that Hail, one of the reasons it's in Spark and not something else is because the user can fire up a PySpark window and type stuff in. And it's this data exploration, which doesn't really work well in a batch environment. So I think some level of interactivity is really important.